Okay, we're going to start on waves. I'm going to give you a couple of definitions and then we'll do examples. I think you're going to find waves are fairly easy, and some of this you may have heard before. Up here we have a picture of a wave, and this is actually more than one wave, and it's got the parts of a wave labeled. So what you basically need to know are wavelength, and I will define what these are: wavelength and amplitude, period, and frequency. Two parts of the wave that are not labeled on here are the peaks and the troughs. So the top would be the peak or crest. That's a C. And then the bottom part of a wave would be a valley or a trough. So top part of the wave is the peak, bottom part of the wave is the valley. And again, you might hear me use crest or trough, same things. So what is the wavelength? A wavelength is, this would write, the length of one cycle of a wave measured in meters. So the symbol for wavelength is lambda. So it's that funky symbol right there. And the unit for wavelength is meters. The reason it's meters is because it's a length. You can also think of wavelength as the distance between two successive points. So in other words, a wavelength would be from peak to peak, from trough to trough, from midpoint to midpoint, as long as it's from the same two consecutive points in a wave. So again, wavelength is the length of one cycle of a wave, and by cycle we mean two consecutive points of the same thing. So center to center, peak to peak, trough to trough. Any of those are wavelength. The next thing you need to know is amplitude, and amplitude is distance from equilibrium, and I'll show you what that is in a minute, to the crest or the trough. Another word for amplitude would be intensity. So how strong is the wave? Equilibrium is this dotted line right here. And all that means is that that's where the wave would be at rest. So if the wave was not moving, if it wasn't carrying energy, then it would just be straight along this line of equilibrium. So the amplitude would be the distance here. This is also considered an amplitude. So amplitude is here. Amplitude can also be here. So from the equilibrium to the peak or the equilibrium to the valley. Period and frequency we have seen before when we were dealing with circular motion. So period is the time for one cycle. Unit is T, it's measured in seconds. So you've seen T before when we did circular motion. And then frequency is the number of cycles per second. And this is measured in hertz. And again, we have seen that before. The unit is hertz, the symbol is Hz. Period and frequency are related because they're inverses. This stylus is not working out very well. Let's try and spell this again. Inverses. So T equals 1 over F, and F equals 1 over T. So in other words, the period would be the time that it takes for a wave to go from crest to the next crest at a certain point. The frequency would be how many times in a second the wave passes through. So they're inverses of each other. Pretty simple to use. Again, none of this is very, very complicated when it comes to algebra. And then the one thing I forgot to mention, I'm going to actually go back up to the top. What is a wave? A wave is the movement of a medium. So a medium just means material. Due to a transfer of energy. So in other words, you see an ocean wave. The water is the medium, and the wave is due to energy moving through that water. A sound wave, not sound energy, a sound wave is due to energy moving through the medium, usually air, not always, but usually air, and then entering into your ears. That's what makes it sound. So if a tree falls in a forest, it doesn't make a sound. Other common mediums would be any kind of fluid. It doesn't really have to be water or air, but something that energy is going to be able to move through would be a wave. Okay, so we've got what a wave looks like, what a wave is. We've got the parts of a wave. So, that's going to go over it. Peak, crest, the valley or the trough, the amplitude, what a wavelength and what the equilibrium are. And then we look at properties of waves such as period and frequency. So now let's look a little bit further at the two different kinds of waves we can see. So the first type of wave are longitudinal waves, and the longitudinal waves are these ones. And longitudinal waves don't look like your classic waves. So what they are pulses that travel parallel to the velocity of the wave. They travel along, so long the wave. And an example of a longitudinal wave would be sound. So the way a longitudinal wave works, you've got these little bunched up parts, and then you've got these spread out parts. So what's happening is particles are getting displaced but parallel to the motion. So they're getting either squished together or spread out. That's contrary to a transverse wave. So a transverse wave is your classical wave. The classical wave shape where you're going to have peaks and troughs, a very easy wavelength to find out. So like wavelength would be here, and then it'll have a distinct equilibrium right down the center. So what is a transverse wave? It's when the wave motion is perpendicular to the velocity of the wave. So transverse waves, like I said, are your classic waves. That's what the example in the last slide looked like. And that's what most of your waves will be. So your ocean waves would be transverse waves. Again, this would be like sound. And this would be like ocean waves, light waves. They would be transverse. Okay, now let's look at velocity of a wave. Velocity is the length of, wavelength is the length of a wave, and frequency is how many waves there are per second. So put them together to find velocity. And we're going to actually take a step in between this. So we know that velocity equals displacement over time. The relevant length would be the wavelength, so that's my lambda. really struggling with this stylus today. Lambda over t, which is period for a wave. We know that t equals 1 over the frequency, so this becomes lambda over 1 over the frequency, which equals lambda times the frequency. So, I'm out of room. Actually, I'm just going to write it down here. Velocity of a wave equals wavelength times frequency. It is also equal to wavelength over period. So lambda is the wavelength, f is the frequency, and v is the velocity. But because frequency equals 1 over period, we can also say that speed is equal to lambda over t. So your medium's not actually moving, and we saw this, or we will see this if we didn't do it yet in the lab. The ocean waves aren't moving. I'm sorry, the ocean itself's not moving. You've just got that energy traveling through the ocean. Same thing with a slinky. The slinky itself is going to go back to where it started from once the energy moves through it. So it's not actually moving, it's just being temporarily displaced. Okay, let's look at 2 little practice problems. The middle C has a frequency of 262 hertz and a wavelength of 1.3 meters. What is the velocity of a sound wave? So we are given that frequency is 262 hertz and wavelength is 1.3 meters. And we want to find velocity. Very, very simple. V equals lambda f, so this equals 1.3 meters times 262 hertz. 340.6 meters per second. 2 sig figs, so V is about 340 meters per second. Easy, easy equation to use. Okay, next one, light moves at a speed of 3 times 10 to the 8th meters per second. A radio wave has a wavelength of 1.2 meters. What is the frequency of the wave? So we know that the speed is 3 times 10 to the 8th meters per second. We know that the wavelength is 1.2 meters. We want to find the frequency. So again, using V equals lambda f, V over lambda equals f. 3 times 10 to the 8th meters per second over 1.2 meters equals my frequency. 2.5 times 10 to the 8th hertz equals my frequency, so 1 sig fig. Frequency is about 3 times 10 to the 8th hertz. Very, very simple equation to use. Okay, 2 more examples, just looking at graphs and what waves would look like. Not really graphs, just more of a what waves would look like on a graph. And then that's it. We'll get to practice tomorrow. Okay, so here it tells us that the wave below has a velocity of 50 meters per second. We want to know the frequency, wavelength, amplitude, and period. So looking here, just to kind of identify the parts of a wave, we're going from crest to crest. That would be 1 wavelength. So looking at the graph, lambda equals 2 meters. And really you could look between any 2 successive points. This was the easiest to find. So crest to crest, again, you're going from 2 to 4, 4 to 6. All of those wavelengths are 2 meters. We're also looking for the frequency, the amplitude, and the period. So the amplitude is going to be easy. We're again just reading that straight off the graph. The amplitude is from equilibrium to either the crest or the trough, so it's 6 meters. So the amplitude equals 6 meters. The frequency, we have the speed. We know that frequency will equal v over lambda. So 50 meters per second divided by 2 meters. And this equals 25 hertz. So frequency equals 25 hertz. And the last thing we're looking for is the period. We know that period equals 1 over the frequency, so this equals 1 over 25 hertz, which equals 0.04 seconds. So t equals 0.04 seconds. So just practice looking at a graph, knowing how to read the graph. Again, this was just meters versus meters, so it just mapped out what path the wave was taking. Let's do one more. If you feel good with this, stop now. Again, this is just going to be a quick one. So now we have a wave that has a wavelength of 10 meters, and we want to find the velocity, frequency, amplitude, and period. So similar to what we did last time, it gives us the amplitude, so we can look very easily here. So from this point to equilibrium, my amplitude is 5 meters. The velocity we'll get from the frequency and the wavelength, or the period. So our wavelength we know is 10 meters, and our x-axis this time is in seconds. So the period is the time it takes for one complete cycle. So in other words, the time it takes to go from, say, crest to crest. So looking at this, we can go from, this is probably easier, from equilibrium back to equilibrium. So looking here, the period is equal to 2 seconds. My frequency equals 1 over the period, so 1 over 2 seconds, that way. So this is equal to 0.5 hertz. And then we know that my speed equals my wavelength times the frequency, so this equals 10 meters times 0.5 hertz, or 5 meters per second. So wave speed equals 5 meters per second. I don't think anything about waves are hard. It's very basic. That's why we don't spend a lot of time. We'll do probably just one day of practice using these equations, knowing the different parts of the wave, and then we'll move on to the Doppler effect, and then we'll be done. So this is it.